This is the 9th lesson for electricity and magnetism. We're getting close to the end of the chapter. Today we're going to take a closer look at how electric motors work. We're going to look at an issue called back EMF, back voltage, and something called counter torque. Both issues that relate to motors and generators. As always, let's just take a second and review what we know so far for the chapter. Permanent magnets have north and south ends, where magnetic field comes out of the north end, wraps its way around to the south end, and a compass will always show you the direction of the magnetic field at any point. You can make magnetic field two different ways with electricity, the long straight wire or the coil of wire. The coil works way better. There are two ways that you can apply force using magnetic field, either on a single charge or on a current. And we've now seen that there are two ways that you can generate voltage using magnetic fields. It's really the same thing, but maybe I should say there are two ways that you can calculate that voltage. If you see a coil when you stare at the story, if you see wrap a wire around like that, then maybe this equation might be the best way to go. But if it just looks like a bar of wire that's moving, then the BLV is often the nicest way. So today we're going to talk about what happens with an electric motor, maybe attached to a table saw when you start running that motor, and then maybe when you start increasing the mechanical load on it. Like what happens when you start shoving a nice piece of hardwood into a table saw and that motor starts to slow down a little bit because of all of that friction as it rubs on the wood. And we'll actually see what happens to the current and the voltage with the motor. But this is kind of the main topic of the day, is the different conditions that the motor might actually be running under. Now I'm just going to make this a little bit wider here where you can see it a little bit better. I'll start filling these notes in. So part 5, back EMF and counter torque. We've already seen that motors can be operated in reverse to make a generator. Yep, okay, that's true. But I don't want you to have the impression that, it can just be one or it can be the other. It turns out these devices, they are both a motor and a generator at the same time. So let's put that in here. In fact, I'm talking about motors and generators, they are both at the same time. You can't say, oh, I only want you to be a motor today, or I only want you to be a generator today, right? It actually has this kind of dual life where it's doing both things. And on the first page here for part A, we're going to look at how a generator is also, unfortunately, a motor. Okay, and it's going to be a motor that's running backwards. And then on the next page, we'll look at how a motor, like on a table saw, is also a generator, okay, kind of running backwards. Now, I don't want you to have the impression that there's actually two physical devices there. This is a metaphor. I went to Google, grabbed an image of an electric motor, and then I copied it twice. But I did that because I want you to, at least in your mind, metaphorically, look at this and go, oh, okay, there are two different roles here. And I'm going to put this one as being my generator, and this one here as being my motor. And we can kind of talk about the two different things that are happening there. First of all, let's talk about the ground rules. How does this deal work? Okay, so here are the rules for the day. The electric rules. Okay, one rule is that if the coil is spinning, okay, if for any reason that coil is spinning, then it's a generator. So you have to associate the idea of spinning and generation of voltage. Second rule, if there is current. Okay, so if we've got current in that coil, if there's current in the coil, it's a motor. So whenever there's current, it's going to be behaving like a motor. All right, now, with my crazy metaphorical diagram, let's try wiring this thing up. I'm going to make this a voltmeter over here. Normally you'd put a big V in the center, but I'm going to make that the dial. So let's just say, hey, you're a voltmeter. And these little white holes you see there are actually mounting holes where you could use bolts to bolt this motor down. But I'm going to pretend that those are the electrical connections. So I'm going to make an electrical connection to my voltmeter. That way I can see if my generator ever generates any voltage. Right now it's not, because the story hasn't begun yet, so my needle on my voltmeter is at 0. And I might want to use this generator to run a light bulb, so I'm going to take that voltage on those blue wires and run it over to my light bulb. But I'm going to put a switch in there, right? That way I can turn the light bulb on and off. And I have to go through this metaphorical motor. You'll see why in a minute. And then I can go through my light bulb and then back to my little voltage bus there where I can access the voltage. Okay. So we're just going to go through this like story time, okay? Just like when you were a little kid and somebody was reading a story to you. So we do have these two devices, the generator and the motor, metaphorically split apart. And this is how the story goes. At the very beginning, first thing that happens in the story is you turn the armature, you turn the coil. I'm going to say coil because I can't fit the word armature in there, but an armature is another name for the coil. So you spin that motor like crazy. So we grab this handle and we go, oh yeah, and you just start cranking that handle really, really fast. Okay? Whoa, wait a minute. If you're turning it, then it's a generator, right? That's one of the rules. So here's my connection between my generator and my voltmeter, and my voltmeter is going to be going way over here, right? Showing, I don't know, some value. Let's just say lots, right? So you get lots of voltage. So the second step in the story is an EMF is generated. Because that's one of the rules. If it's spinning, it makes a voltage. So, yep, we're definitely going to have a voltage. But right now, we're not going to access that voltage. I'm going to have my switch just in the off position. Oh, here, I'll draw the switch the same way I drew it last time. Be a little more consistent here. Okay. So lots of voltage, but we're not actually drawing any current yet. Well, that's kind of boring. Let's see if we can actually light this light bulb up. So, the next step. Let's make life interesting. Let's close the switch. In other words, let's turn it on. Okay, so we're still turning this thing. Getting pretty tired turning that thing super fast. So my generator here is going to be making lots of voltage. My voltmeter is going to be going, oh yeah, got lots of voltage here, right? The needle's way over here. Lots and lots of voltage, which is great. And now we're going to close that switch, put it into the on position. And so we'll be able to actually have some current flow through that light bulb. Okay, good news. The good news is light bulb lights up. Fantastic. Little light bulb of science. It's great. And that's happening because current flows. So step 4 in this story, current flows. You could actually calculate the current just with Ohm's law, right? How much voltage did you generate divided by the resistance of the light bulb? Now, this is where things get interesting because at this moment, you've now got current flowing. It didn't happen until you turn that light bulb on. But right here, the story is going to take a little twist because one of the rules at the top of the page was if there's current, it behaves like a motor. So this is kind of the idea of the day is right here, step 5 and 6. The current makes it behave like a motor. And by that I mean it's going to create a torque. That's what motors do. Unfortunately, because of that negative sign in Lenz's law, that negative n, change in flux over change in time, because of that negative sign, because of the way Lenz's law works, that motor will always create a backwards twist. So the motor makes a backwards, we usually just call it counter, but it creates a backwards counter torque. And that's going to try to slow the motor down. This is why you can't actually attach a generator to a motor and then hope to power the motor by the voltage coming from the generator. It turns out as soon as you try to do that, there is this backwards force on the generator slowing it down. And it's just it's conservation of energy. You can't get something for free. And as you try to run that doomed experiment of attaching just a motor to a generator and having it self-power itself, the generator creates this backwards torque and just slows itself down. Okay, well that's the first half of the theory for today. Now let's look at it the other way around. What if I am trying to run some table saw with some voltage? It's plugged into the wall, right? 120 volts. It's got some source voltage to it. And I want to run my table saw and see if I can then put a piece of wood through the table saw and see what happens electrically in the story. First of all, again, the idea of it being split apart, this is metaphorical, right? This time I'm going to put the motor here, that's the main job, but we're going to see that it's also a generator. It's going to behave like a generator in reverse. The wiring, okay, some metaphorical wiring. This is going to be my source voltage, V source. It could be like the wall voltage. You know, your 120 volts. I'll put a switch on it for safety so we don't have to have the motor running all the time. And then we're going to go through this little mysterious gray box back to the wall voltage. Turns out that gray box is actually going to be some generated voltage by the idea of it being a generator. Okay, well let's go and run our table saw. So at the beginning the table saw is just sitting there, it's all nice and quiet in the garage, and you're like, okay, let's get this thing going. At the beginning the blade is not spinning, okay, so it's just sitting there kind of in the off position, so no spin yet. And then we're going to go and turn this thing on. So very first step number 1, you connect the motor to the source voltage, the powering voltage, right? Whatever you're going to use to run the motor. It could be the outlet in your wall. Okay, so let's close that switch. Let's turn this motor on. So here's my source, here's my switch, which is now in the on or closed position, and through the little mysterious gray box back to our source. So again, V source. What you're going to find is at that moment a dangerous amount of current flows, just a ridiculous amount of current flows. So I'm going to put in here lots of current flows. And if you wanted to know, well, how much current flows, you could just do Ohm's law, right? You could say, okay, yeah, what's the value here? The current would actually just be the source voltage divided by the resistance of the coil. And it would be a current, to be honest with you, that is so large that at that level, the circuit breaker in your house will eventually trip, right? It's probably going to be way more than this circuit can handle long term. Maybe for a few tenths of a second will be okay, but we don't want to have that much current flowing all the time. Okay, well, why do we do that? Well, the current is making this thing behave like a motor to create some torque. So the current lets the motor make a torque. Okay, so there is going to be this massive current creating a massive torque on this thing, saying, let's get going, but it's not going yet. So you might look and go, well, why did you say there's torque, but it's not spinning yet? It's like you're in a car, the light's gone green, and you mash the gas. There's lots of acceleration, but you haven't started yet, right? The wheels haven't begun to spin, but you're just starting to get thrown back into your seat, okay? So it's going to happen, but it just hasn't happened yet. Okay, so step 4. This is where you have to be patient for about 0.2 of a second. It won't take long, but we do need to wait for just a little bit. So step 4, the motor begins to speed up. Okay, so it's starting to spin, right? Like, yeah, there's a little bit of spin going on there. There's still a whole bunch of torque saying, let's go, right? Let's get this thing spinning. But at this point, we're only maybe a tenth of a second in, and it's just kind of starting to spool up. But hang on, it's spinning. If it's spinning, it's going to be a generator, right? We've talked about how we've got these two rolls. We've got the motor, and now it's going to be a generator because it's starting to spin. So we got to talk about that issue. The spinning coil it's going to behave like a generator. And it makes a backwards voltage. We call it a back EMF. So let's kind of look at this pictorially here. By the time you get your blade up to speed, this thing is spinning really fast. We've got our source voltage. And it's connected up with an on switch, a closed switch to our motor. But now the generator, right, the spinning coil, is going to create this back EMF. Okay, so we usually just denote that like this. It's also a voltage. You could use two V's here, but we like to use the script E whenever it's a brand new voltage. And it's going to be a voltage that's wired up in the reverse direction. So it will fight the source voltage. Okay, but that comes from the spinning coil. Okay, the fact that it's now going to behave like a generator. So you've now got these two voltages fighting each other, and the source voltage will win, but not by very much. So I like to say this, kind of my own little Mr. Gowe phrase here. I like to talk about the effective voltage. So that's how much we have left over. The effective voltage is reduced. So you're now going to have less current. In fact, here's the calculation for how much current there would be. The current that flows, there's this competition of voltages here. So you're going to have the source voltage minus the back EMF. Then you divide by the resistance. And as that back EMF grows, that numerator gets tinier. Well, if you have less current, remember how motors work. You have to have current flowing in them. So if there's less current, then there's actually less torque. That's why motors don't speed up to some infinite speed. Eventually, they get going so fast that the back voltage gets close to the source voltage, and there's just enough current to create just enough torque. So there will be a little bit of torque left, right? Not much, but there'll be just a little bit of torque left here, just enough to overcome friction. And the table saw is sitting there just going, and it's going really fast. There's barely any effective voltage. There's barely any current flowing. And then you go and take that big piece of hardwood and you push it through the table saw, and the table saw slows down. And when it slows down, it's not spinning as fast. So if the spin speed drops, so does the back voltage. And as the spin speed drops and that back voltage gets tinier, then this numerator actually gets bigger and the current goes back up. And now you've got more torque. And that's why when you hear a piece of wood go through a table saw and it slows down, you can hear that it's getting more serious. It's like it goes from like a noise to like, and you can hear that there's just more torque going on as more current starts to flow in that motor because it's trying to get back up to that nice natural speed that it would spin at. So some key things there. If it's spinning, it's going to make a voltage, and that voltage will actually fight the source voltage. On the previous page, if the current's flowing, then the device is going to behave like a motor, and it's going to create this backwards twist trying to fight against you. Okay, just an example and a half here for today, and then these notes will be done. So what does this story say here? It says a motor has an armature resistance, that's the coil, has a coil resistance of 12 ohms, and it's connected and draws 1.5 amps at startup. That's when you first start going. Determine the back voltage, the back EMF at full speed if the current drops to only 0.2 amps. So you can see those two different current values, right? Very, very different values. Here it is when it first tries going at startup, right? We're just beginning to go. And here it is at full speed, okay? Way, way down there at a nice safer 0.2 amps. Whenever I do these questions, I always like to split my page up and talk about the startup condition when it's trying to go but hasn't got going yet, and then the full speed story. So again, by startup, I mean, if you want to talk about a car at a green light, we're talking light's gone green, massive acceleration, but we haven't got going yet. So that's like when you turn the switch on the table saw and that blade begins to accelerate but hasn't really got any speed yet. Okay, we'll call that the startup condition. All right, so at startup, it is not yet spinning. It's going to in like maybe 0.2 of a second, but right now, not yet. And it does take a spin to make a back voltage, so there's no back voltage yet. Now, this is the equation you'll find on your formula sheet. You can use it all the time as long as you realize that at startup, when we're trying to go but haven't got going yet, the back EMF will be 0. So you just scratch off the back EMF, right? So the equation's fine, but we'll just put 0 in here. And so it's a little bit of a confusing phrase that I've got there, startup, right? Like, yeah, we're starting to go, but we haven't got going yet. Okay, well, if I actually run this equation right now, I can find the source voltage. I can find out what kind of voltage we're attached to with this motor. I've got 1.5 amps of current flowing when we begin to run this motor. 12 amps or 12 ohms for the resistance. Hey, it looks like it's some sort of cordless drill maybe with an 18-volt battery. Okay, now let's take some useful information and wander over to the full speed, we're all up and spinning story. There are a couple of things that don't change between the two sides of these stories. One is the source voltage, so if it's 18 volts at startup, it's 18 volts at full speed. And the other is the resistance of the motor. So if it was 12 ohms at startup, it's 12 ohms now. So those two things go back and forth. Basically what it comes down to in Physics 12 is you're going to use one side of this story to find one of those things that's missing and then carry it over to the other side of the page and keep going. So now I'm going to use the same equation again, and now we're going to go and look for that back voltage. It's probably going to be pretty close to 18 volts, right? Because you generate a voltage that's almost as big as the source voltage backwards. So we'll just substitute and just work our way through the calculations here. As you do, that 0.2 multiplied by the 12 creates this 2.4. That number is kind of interesting. That 2.4 volts is actually what I call the effective voltage. It's how much voltage is left after the back voltage fights the 18. Now a little grade 9 arithmetic, and we're there. The back voltage is 15.6 volts. And you can see where that 2.4 fits in there now, right? If the main battery voltage is 18 volts, and the spinning generated voltage is fighting you at 15.6. There's really only like 2.4 volts trying to operate this motor. That's why the current goes way down to some nice safe value. Now we're going to do just one little follow-up question at the bottom of your page there. You can actually imagine what happens when you take this cordless drill and start drilling into a wall, and the drill slows down a little bit, and it might not be going full speed. That mechanical friction might make it slow down to 3/4 speed. And we can actually figure out currents now for any speed, because what we know is it takes spinning to make a voltage. So that spinning voltage is proportional to speed. If you're not spinning, you have no voltage. Apparently in this story, at full speed, we're at 15.6 back voltage. Well, it's completely proportional. So if somebody said, ooh, what about half speed? Well, then it would be half of the 15.6. We're going to go 3/4 speed. So we'll go with 3/4 of the 15.6, and it turns out that at 3/4 speed, when you're drilling into a wall and the drill bit slows down to 3/4 normal speed, you'll only be generating 11.7 volts backwards. Now remember, we still have the 18 forward push from the source, from the battery, but now the generator part of this deal fights back at 11.7. Okay, there's our equation of the day. It's the one equation we'll use all the time. It's just the back EMF that changes around a little bit. Throwing the values in, the 18 has this battle with the 11.7. The 18 will win, but only by 6.3 volts. And that current is now at 0.525 amps, or if you wanted, you could call it 525 milliamps. And that's where we'll finish up for today. So that back voltage from the motor, it is proportional to how fast you're going. And when you're just trying to start up and you have no speed at all, then you have no back voltage at all.